Okay, let's review the definition of a sunflower. So, a sunflower or delta system with K petals and a core Y is a collection of sets S1 through SK such that SI intersect SJ is Y. So this core, the intersection of any two elements in this set is the core. And any two elements that are not the same. And so if we take away the core from this set, we still have to have other things in the set. So this sets have to be things beside the core, but they all have to pairwise intersect to be the core. And note, any family of pairwise disjoint sets is a sunflower with an empty core. The core is the empty set. So today I'm going to be talking to you about the sunflower lemma. So what is the sunflower lemma? Let F be a family of sets, each of cardinality S, so F is an S uniform set. If the size of F is greater than S factorial times K minus 1 to the S, then F contains a sunflower with K petals. So what is this saying? This is saying that if we have an S uniform set F, that as long as F is greater than this certain size, this size does depend on S, that F has to contain this structure of the sunflower within it with K petals. And let me prove this to you. So I'm going to prove this to you by induction on S. And so for the base case, we have S equals to 1. Since the size of S is greater than 1 factorial times K minus 1 to the 1, which is just K minus 1, and they are all one element sets, and one element sets are disjoint, or also be the same set. Any K of them, since we have strictly greater than, yes, because we have it's a greater than equal to, so we have to have at least K of them, will form a sunflower with K petals and an empty core, which is the empty set. And so the base case holds. Hooray. So for our inductive hypothesis, we restate the sunflower lemma before we assume it for some specific S greater than the base case. And so it's an S uniform set of size F, and we assume it has the certain size and has to contain the sunflower with K petals. So let's consider an S plus one uniform family F, and also has those same size requirements, but with S plus one instead. And so let's take a maximal family A from A1 through AT, so it has T sets in it, of pairwise disjoint sets in F. And so if T is greater than K, that means there's more than K elements within A, then we can just take these sets and form a sunflower take K of them with K petals and an empty core. But let's assume T is less than K minus 1. And then if we have B, which is just the union of all these less than K minus 1 sets, then we have to have that the size of B has to be less than S plus 1, because they're all S plus 1 size elements. So this has to be S plus 1 each of them. And then there's less than K minus 1 because there's less than K minus 1 of them. So there has to be this amount of B. And the pairwise disjoint, so they have to have different elements. So they can't overlap. And so by the maximality of A, the set B must also intersect every member of F. So any element we add to it must also intersect it. And so we can kind of partition these elements. We not partition them, but split them up based on what elements they intersect with in B. And thus, by the pigeonhole principle, there must be some point X in B that must be contained in at least the size of F over B, because if you kind of split them up in this amount, and so like we can know X is going to be in at least the size of F over B of these sets, and this is S plus 1 factorial to the K minus 1 to the S plus 1, which is by our assumption on F is. And then we said B is S plus 1 to the K minus 1, which you showed earlier, at least that size. And thus, we have to have, when these S plus 1 factorial cancels out, we get this S factorial again here. And then when we have the K minus 1, which cancels out with this K minus 1, the exponent cancels out, and then we get this S here. And remember our inductive hypothesis, just remember our inductive hypothesis. And so if we remove X from the sets that contain it and consider this family F of X, where we have S sets S in X, and we remove X from them, and this sets in F and X is in S. So we have K minus 1 of them because we have the size of those, and now they all have size S. And so by inductive hypothesis, they have to have a family of k petals. And so if we add x back to these sets, and so now we still have k minus one of these, we still have k of these sets, we still have this k minus one of these sets, but now they're all s plus one uniform sets, and so this set is now a sunflower in the original family because it was an original sunflower, but it had size s minus s, but now we added one more set to it, and so it now has size s plus one, and so now it's a sunflower in the original family, and we've proved it. Yay! And so the sunflower lemma just beautifully states that once you have sets of a certain size, we have to have this kind of beautiful structure within them, this kind of intersecting, self-intersecting kind of sunflower within them. And so that's very wonderful.